So just to get a quick grasp of the audience, how many people here have ever written a piece of code in Solidity, even just for playing? Okay, cool. How many people here have ever written unit tests in Solidity using Forge or Foundry? Okay, what about Hard Hat, Truffle, something else? Brownie, something like that, okay. Did I miss anything in terms of the frameworks? Okay. How many people here have ever done test-driven development on smart contracts? Okay, so I come from the world, so in my Web 2 days, I wrote a book called Art of Unit Testing, and I'm a big proponent of test-driven development. So, and when I got into the world of Solidity and smart contracts, it scared the hell out of me because you cannot change the code after you deploy. So the unit testing becomes much more important. So I quickly learned that test-driven development is actually much more useful to me on smart contracts because it actually gives me much more confidence in the code. So today I'm going to teach you, I'll at least give you a glimpse of two things. So we have about 40 minutes. One is how do you write tests directly inside Solidity using a framework called Forge. And the other is what does test-driven development look like? And if you have questions, feel free to ask. Worst case scenario, I'll tell you that we'll talk about it later. Okay. So as I said, I wrote a book called Art of Unit Testing. So everything I'll say here is kind of based on that book, but I wrote it in C#. And after that, I rewrote it in JavaScript. And now I'm thinking of rewriting it in Solidity. But unfortunately, all of the lessons that apply to Solidity, sometimes they don't make sense in the other languages because blockchain paradigm changes how we usually write code. What I've noticed is that it's actually useful enough. So I've decided to kind of go upon this journey where I'm going to actually do training to people about this stuff. So if you're interested in doing some of this training as well, I've started a course. You can see it down there where you can actually take a full day version of what I'm going to show here. So I'm going to actually start with talking about the test frameworks and then the TDD process and the origin. And then we're going to do a quick demo. We'll see whether we'll do it live or I'll just use screenshots depending on how much time we have. The first important thing to realize when we're writing tests or unit tests is where they are in this diagram. Whenever we write tests to any piece of software, we have to realize that there are tests at the top that bring us the most confidence. So this is the end-to-end test. For example, when you're using the user interface and stuff like that. And at the bottom, we have usually tests that run in memory and they just test specific functions. And when the lower you go, usually the easier it is to write the tests because you have less moving parts, but you also gain less confidence. The test will usually run much faster because you don't have to load a web application maybe or something like that. But you will actually, you can gain a false sense of confidence if you only focus on the bottom, and you can gain a very long type of feedback loop if you go on the top only. So a big anti-pattern that I see in many organizations is that they only choose one of these levels. They start with one of them and they feel comfortable, and then they just stay in that level. For example, they just do unit tests or they just do end-to-end. The problem with end-to-end tests is that the first 5 give you 95% of the confidence you need. But then you write 50 more or 100 more. And each one of them takes exactly the amount of time that the others took. So it might take 3 minutes to run. So then it takes hours and hours to run all the tests at the top. And they break very easily. They break on every little thing. So there's a lot of noise. And so you are very frustrated because everything breaks all the time. And most of the time, it's not important. And until you find it out, you're wasting a lot of time. But if you go the other way, you might have all the tests green and they always pass, but your application does not work. So usually the combination that I recommend is that you have a lot of tests at the bottom and very few tests at the top, but it has to be a combination. You cannot choose either or. It has to be almost a 10-to-1 ratio between different layers here. And I will make the slides available for everybody here. In our world for Solidity tests, we're actually mostly going to go with the bottom 3 layers here. So I will show how to write what looks like unit tests that actually run inside Solidity, so a smart contract calling another smart contract. The way it's going to work is that we're actually going to write a smart contract which just happens to also do asserts. So it's going to call other smart contracts, that's our production code. And we're going to have smart contracts that are test code. And I find that it actually makes things a lot easier and more readable. And I come from a world where I did the same thing with hard hat, a lot of these tests. And now I'm almost 90% of the time I will write tests only in Forge because it's much easier and cleaner in terms of pure readability and just writing much more quickly. Now, writing tests is just a specific skill. Actually, when we're talking about test-driven development, it actually requires 3 different skills to succeed. So the idea of writing good tests is just one of them. Writing the tests before you write the code is a second skill, which means you can write really crappy tests before you write the code, or you can write really good tests after you write the code. The quality of the test is a separate skill, and when you write it is a second skill, and the third skill is design. And design is a skill that we learn our whole lives as professional developers. But design is also one of the biggest walls for a lot of developers that want to start test-driven development, because every problem that they try to solve, they actually start with tests, but then the design of how to solve that problem can be, it's a very open question. So it's really important to come with at least some design skills into this, or you can create a really working application with a really bad design, which means that it works at the beginning, but then when you try to change it later, it's going to be almost impossible to change. I'm sure nobody here has ever tried to change an application. It was very difficult, right? Any developer here that has code that they're afraid to change today? So that's how it starts. It's a design skill. It's a separate thing. So those are the 3 things. I'm mostly going to talk about the middle part and the left part. In terms of the tooling I'm going to use Foundry. It's actually a suite of different tools. We talked about some of them in a previous meeting, but today I'm really going to focus on the actual test code. At the bottom, you see that basically every test that tests stuff on smart contracts needs to run on some sort of a chain. And all of them come with a chain simulator. A very common one is called Ganache. If you probably used it if you used Truffle or if you used Hard Hat. In Foundry, there's another one. It's called Anvil. It's really, really fast, but it's very much like the others. It's not really important for our purposes. You just have to know that when you're running the tests in Foundry, it uses Anvil under the covers. And you can also run Anvil separately as its own little blockchain on your computer. And then you can simulate things on top of it. In fact, if I go back into this, at the API test level, or at the end-to-end level, you would have to run it locally on your computer, or you would actually have to access a node somewhere outside your computer to have some sort of a chain. And at the end-to-end level, you will use a testnet, which is just another node in another blockchain that somebody else set up. But locally, it's much faster. And if you need to use some of the smart contracts that exist in a testnet or in production, let's say in Ethereum mainnet, then you can use this idea of forking, where we can simulate those external smart contracts as if they are locally on our machine. And this is very, very useful, especially if you're writing smart contracts that have to interact with smart contracts that you didn't write, like DeFi protocols or anything like that. So forking comes in very easily as a parameter that you can put either inside your test or as a command line, which means that if you try to access a specific address where a smart contract actually lives in the mainnet, it will magically work on your local machine, and you can actually run transactions on it. So you can simulate a lot of things. So if you're ever wondering if people that are building these DeFi protocols that interact with other DeFi protocols, how they test it, they use forking almost all the time in all their tests because they have to check the integration between the smart contracts. The other thing that happens is that um, we can also simulate balances of different currencies if you have tokens. So we can use the tools to basically fake our balances of a specific token. We can fake what type of user we are. We can decide that we're calling a function of a smart contract from any address. We can take over any address that we want, including addresses that we don't have control over in the real world. So if I wanted to, and this is very common, if I wanted to simulate or mint new USDC tokens in my tests, I can do it. It's very, very easy. There's like a pattern to do it. Basically, you take over and you call mint because you're the owner. So you just call the function as the owner of the original smart contract. So you can simulate almost any situation. In many ways, it actually simplifies writing tests on smart contracts, because if you have a specific state of the chain and you call it with a specific variables and specific parameters to a function, you will always get the same result. We don't really have threading issues or stuff like that. We don't really have race conditions because the blockchain takes care of a lot of complicated logic, so we don't have to take care of it. So in many ways, we just have to worry about the logic and the integration, which is, even for the most simple smart contracts, it's really complicated, because if we screw it up, it's going to be very hard to roll it back. And if we have to roll it back, it means that we are more centralized and we have to choose. So depending on our centralization choice for the code that we wrote, we might specifically create something that will be really hard to roll back because we want to give users trust. So it's a let's call it an economic choice, a freedom choice. And projects that decide to be more centralized will be closer to the world of, let's call it, continuous delivery, which we're used to in Web 2. And projects that are less centralized and more decentralized, where the contracts are also more immutable, are going to have a harder time doing continuous delivery, because they can't just keep rolling out new versions of the same function and update it, because they can't. They actually have to create new versions of the entire smart contract, deploy it, move storage around. So it's more complicated. And we will not talk about which one is worth it, because it's more of a philosophical view of what you want to create. Okay, so just like if you've ever written a test in any other programming language, it looks almost the same when you're writing it in Solidity. Every test in the traditional world will have 3 parts: arrange, act, and assert, in that you set up some state, you act on that state, and then you assert that something is true or not true. This is an example of how you'd usually write tests in hard hat. You would have like these describe blocks and then an it block, and then you would call something. So for example, if I was using hard hat, I would write a code like maybe something like this, where I use the hard hat library and I deploy a contract and I write this in JavaScript. And I'm showing you the JavaScript because I'm going to show you how it might look in Solidity in a second. I want to compare those two. So the first thing whenever you want to run a test in hard hat is that you actually have to deploy all the contracts first. And then this is an example of what a test might look like, where you await deployment and then you send a transaction with specific values, and then you call maybe another function like get balance, and then you expect, using this special assert, that we get a format of ether to equal this. So what I want to emphasize here is that this is very, very wordy. There is a lot of text here for something very, very simple, because we are using the world of JavaScript to interact with the world of smart contracts. So everything has to be converted from one side to the other. If I want to send 1 ether, I have to parse ether using ether's library to convert the string 1 into something that's acceptable on the other side, and the other way around as well. So everything is more complicated. It works, but everything is very verbose. Right? This is an example of what it looks like together. This is the same test if I was using Forge and Solidity. Okay, I just write a contract. I have a name for the test. We'll talk about the naming in a second. I literally just instantiate the new contract. I call it, and then I assert equals, which is a function that I inherit from the base contract, which is called test. This is the entire test. There is no need to deploy anything. That's taken care of by the test runner. Everything is inside of Solidity, so I don't have to convert 0.1 Ether. I just call the functions. I'm just another smart contract calling another smart contract. This is using Forge, okay? Or more likely, it's using Foundry. Forge is, to run this, I would write Forge test in the command line. And this would automatically compile all my tests and all my smart contracts. It will detect my test because it starts with the word test, okay? So your tests here have to start with the word test.
Maybe a few words. What is Forge?
Forge is it's an open source tool, a suite of, it's one tool which is part of a suite of tools called Foundry, which is a competitor to Hard Hat. So if you want to develop smart contracts, you can choose Foundry or Hard Hat or Truffle or Brownie. They all exist and they work in parallel. So Foundry is relatively new. It's one of the newest ones, okay? So if you were in JavaScript, you might use something like Jest as your test runner. But here you're using something like Forge. Okay, so Forge is the test runner and the command line. There's other tools as well for debugging and tracing, which we will see. So this is just a test library as far as we're concerned. But it's also a command line test runner. Other questions before we continue? I want you to notice the name of the test here. Actually, the name of the test is very important because it helps with the readability. Whenever we're building something, we want to make sure that the people that are going to read the stuff that we wrote will not want to murder us. It's really, really important. So imagine that you're looking at the code that somebody wrote 6 months after they've already moved to the next company. And you have no idea. It's called like test 1 or test 2 or test works. I'm sure nobody here ever wrote tests like this. But I've seen them. They exist. So we actually have to pay a lot of attention to the names of the test. And I usually use 3 parts in the name of the test. It really doesn't matter what language I use. The first part is usually the entry point, the thing that I expect to work. In this case, it's the receive function. The second part is scenario. So imagine I'm writing a sentence in my head. If I call receive and I'm using it to send funds, then I expect it to do something. And the last part is the expected behavior. It updates the balance. The name is important because when you run tests in any type of tool and a test fails, you will not see anything except the name of the test and maybe some trace. But the name of the test is going to be the first thing that you see. You will not see any comments. And when you have dozens or hundreds of tests and you have the good names for the test, a lot of times it actually prevents you, not prevents, but you can avoid actually go and read the test. You can actually go directly to where the production code problem is if the test name is good enough. But if the test name is really bad and something fails, you actually have to go into the test and start reading it and understanding it. So the more readable your test is in terms of naming and inside it, the more you can actually give people the ability to avoid reading your test and actually go directly to the problem. Does that make sense? So if you have 3 tests failing and they all have this naming convention, you now say, oh, this thing works, it fails here, and also with this scenario and with this scenario, but all the other scenarios are passing. So maybe I know where the problem is, just by looking at the names. Questions? Answers? Okay. I'll show you what it's like to start with your first test. I'm gonna use a tool called Forge Init. Did we actually fix the, Shauli, did you ever find the microphone? I will scream. Let's see. Let's see if this works. Okay, everybody. Can you hear me? Yes. Good. I'm actually going to go here and I'm going to, in my code, I'm going to clear. I'm going to create a new folder, call it demo 9. Just a new folder. It's clean. Right? This is everything inside the folder. And I'm going to call forge init on this folder. Forge init will basically create the first couple of test examples in my folder and initialize a new project for me. So if I open this now in VS Code, you see that I have a source folder with an example smart contract. And I actually already have a test that shows me what it's like to write a test. So just to go over this really quickly, it's a really simple smart contract. Just who here has experience with Solidity? Just raise your hand. Okay, some people do not, so I'm going to go really quickly to explain what's going on here. It really looks a bit like JavaScript plus Visual Basic if you've ever had the nice experience. A contract just has a name. It has a public storage variable. This is really important. This is not a regular in-memory variable. This is actually a variable of type uint256, which is stored on the blockchain. So when you change it, the only way to change it is from inside the smart contract. And when you read it, you're actually reading from the blockchain. And when you read it, you're actually calling a function called number. This will be represented as a function. And then we have a set number that takes a parameter of that type, and it's public. Anyone can call it. Anyone can call it. We don't have any limitation on who can call this function. But whenever we're setting the number to a new number, what's really happening is that we're going to have to change storage. Whenever you change storage on the blockchain, you will actually have to do it in a transaction. So a transaction is the thing that changes the state of the blockchain. So to change it, the only way to do it is to actually sign a transaction. Incrementing is also changing the storage, so it requires another transaction. From the point of view of Solidity, it doesn't look like a transaction. But if you were doing it from a front end, it would actually pop up your MetaMask, and you would actually have to sign a transaction, and it would cost you gas to do this, calling these functions. In fact, every time, if you've ever minted an NFT, you were just calling a function, and you were changing an ID number inside the storage of that smart contract. And so even if the NFT was free, it would still cost you some gas, some money, just to run this simple minting operation. So NFTs are really, if you've never written an NFT, I highly recommend that you write your first NFT this week. It is the hello world of Solidity as far as you're concerned. It sounds like it's a simple thing, but if you try it, you will realize there's a lot of stuff involved with it. At the base of it is just a number that keeps changing, and my ID is mapped to you, and this other ID is mapped to another person. But then you have all these mechanisms that make sure that who can transfer, who can move, and all these things. But they're all just functions that change storage inside on our blockchain. The tests are also relatively very simple. We are importing Forge standard library. We have a test base contract. Actually, okay. We are importing the Forge standard library, which is a base contract. That's a lot of pizza. I like it. And we are importing our, don't worry, in a few minutes, which is probably about 10 or 15 minutes, we will take a break and you'll be able to grab some pizza, I promise. Don't kill me. So we are also importing from our source directory our actual production code. So our test is inheriting from the test smart contract. It actually has its own variable, which is the counter. So we're just declaring the counter publicly here. And we have a setup function, which you should know if you've ever written any test in almost any other language. The setup function happens once per test. So if I have 3 tests in this class, then the setup function will be called 3 times. And in the setup function, we are actually initializing counter. We are actually deploying a new smart contract based on counter. So when you see the word new in Solidity, what's actually happening is that we are actually allocating a new smart contract with its own address on the blockchain. So new is actually deploy. And it all costs a lot of gas and money, but in our test, it doesn't matter. It all runs locally. So it feels like you're just creating it in memory, but really what you're doing is you're deploying a new contract into the blockchain locally. And then we're calling set number to 0, and this happens per test. So now we have 2 tests. We have test increment, which is a terrible name. It's a terrible name as an example because it only talks about the entry point, but it doesn't say under which conditions and what is the expected behavior. So if you see those names and you have those names, try to add more context. And remember, the motivation here, I'll give you another motivation. Imagine that the person who's going to read your test is a serial killer that knows where you live, okay? And you do not want them to ask you any unnecessary questions. So you give them all of the information up front. If they say test increment, okay, but what's supposed to happen? They'll come to your house and ask you what's supposed to happen. Or they will not have the patience to go and actually read the test if it's a long test. So we call increment, we assert that counter number. You see this is that storage variable, but it's actually a function. We're asserting that it's equal to 1. So it's actually very, very straightforward. How do I run this? Well, actually I'm going to run it from here. Let's see if that works. I'll run it from my terminal. I'm going to write forge test. So that's compiling, and it's running all my tests. And I have 2 tests that are passing. Now, what if I make a mistake? What if there's actually a bug in my production code? Let's actually put a bug in here. Let's not increment this. And I'm going to run forge test again. Actually, I have to save. And I'm going to run forge test again. Now we should see assertion failed, which is good. And now I like to work in a continuous test mode. So what I'll usually do is I'll actually do forge test and then -W for keep watching. So it will continuously run whenever I change the file. So now this will run, it will give me all the information. I'm going to undo this for a second, and I'm going to save. And you see that it automatically runs my tests. I'll redo this, and I'll save. And you'll see that you might start to see a problem here. It just says assertion failed, but it doesn't say what failed. So we can actually change the verbosity. So you say -V, that's the default verbose, but you can also do extra verbose. You can actually go up to 5. This is just the default the second level. Second level, you start to see, oh, I expected 0 but got 1. Or I expected 1 but got 0. What if I do 3 levels? Now it shows me the function and the trace of the failing test. So it says, oh, we even have emit of a specific event, the values, and the log, right? So we can actually see what's going on here. What if we do it, what if we add another? Let's see what happens now. Accept modification? Yeah, I guess. So now it traces all the tests, including the setup functions and everything. And this is really, really helpful because when you're getting into more complicated code, I'll give you another example that I highly recommend that you do. If I, come on. If I, in my tests, what I really like to do is I like to do something like, there's a thing called, there's a lot of cheat codes that you can use. And the cheat codes are enabled using this thing called vm dot something. So here I'll say vm dot label, and I'm going to say that the address of my counter, it's really hard to program with one hand, but the address of my counter, I'm going to name it Bob. And I think that syntax should work. I haven't actually tried it in a while, but let's see if that works. Okay. Now, why is this important? Because now, instead of just an address, I can actually see Bob, somebody called Bob.number. Okay, so my traces actually include the names. And this is really, really important when you have multiple smart contracts working with each other, or you're creating these new ones, etc. So vm.label is a very, very powerful kind of thing. Questions so far? Okay, that's pretty cool, right? Let's see if we missed anything. Okay, so now we can get into some of the, so this, we haven't even done TDD yet, but I'll show you a couple of other cheat codes. You can, for example, decide that the next function call is supposed to throw an exception. So you can say VM, I think it's called expect revert. So you can say expect revert with some message. And what you're saying is that the next, when I call this, I should actually be getting a revert from this smart contract. So if I save this really quickly, I should actually see that the test fails because I did not get a revert, right? So I can check a lot of different things. I can also decide that I can do like vm.prank, not plank, but prank. And I can say that from the next call is going to be executed from another account. So if I'm calling Bob and I'm allowed to call Bob, I should have one behavior. But if I'm calling Bob but I'm not allowed to call Bob, I should get a revert, right? So how do I simulate it? I use VM prank as an example. We can also do, we can move back and forth in timestamps by using warp. And we can also deal ourselves a lot of ether by calling deal, like a dealer, giving people cards. And we can do a lot of these really, really cool things. So you can simulate a lot of different situations pretty easily. Any questions? Okay. VM, it's a helper function, it's a helper object that we inherit from test. Okay? So it's built into here.
So where we can see all the functionality in the VM?
Well, you can literally go to the code. So all this code is, I think it's supposed to be inside the lib here. You can see in Forge STD, you'll see the lib and the source. You can actually see all of the, so it's, what we're seeing here is actually STD cheats. You can see all of the cheats that exist here. There's a lot of code, but actually what you want to look for is Foundry book. If you just Google Foundry book, there is a lot of good documentation here. So these are some of the functions. I'll give you another really, really cool, important tip. You can actually have tests that you see here that actually have parameters in them. And what's happening in this test is that Forge automatically sees that the test is a parameter, and it will start calling it with a lot of different values automatically for you. It will do fuzz testing for you. And you can also then limit those values into vm.assume. So using these functions, you can say, would values between 1 and million, call this function 256 times or 256,000 times. You can control a lot of these parameters through command line or through the code, which is really important when you want to get confidence in your code. Yes?
Would you recommend on the source
Sorry?
Would you recommend on source for templates?
Source for templates, like for the tests. If you want to see good tests, you look at some of the well-known projects like Aave, and there's a bunch of them. Now I forgot all the names suddenly. I don't know why. But if you look at all the big projects, they have all their source open on GitHub, and you can actually look at their tests. You will see a lot of really cool stuff. For example, you'll see that a lot of them actually combine Solidity tests with Forge with hard hat, which is also what I do. Because you still want some tests at the upper level using JavaScript because you want to test how it works as JavaScript integration. Deployment is a bit easier. So you'll see that a lot of projects have a combination of Forge plus hard hat at the same time, but it's a different combination. So that's where I would look for. There aren't a lot of templates, but there are some really good projects out there. Okay, just maybe a couple of simple examples. I'm actually going to skip the live coding, but I'll show you what TDD looks like, and then we're going to finish. Is everybody okay? We're doing it in 5 more minutes? Okay. Test-driven development is actually comprised of 3 different steps. The first step is that you don't actually write a piece of code without a failing test. You don't write production code. You actually start with a test. So you actually make it fail, then you make it pass without touching the test. You have to make it pass through the production code, and then you can refactor. You can change the code because everything is passing. Those are the 3 steps, but this is very simplistic. This is usually how I explain this. You always start, you write a test to prove the next small piece of functionality is missing or wrong. Imagine that your definition of done is that you're writing a test that has to pass, but the feature doesn't exist yet, so it's a bug. The bug is that the feature doesn't exist. Okay, that's a bug. So we're proving the bug by trying to call the feature that doesn't exist yet. It's really weird at the beginning when you just start, because you're actually starting from a test and the code doesn't exist. So you're just looking at the screen, and the screen looks back at you, and you're like, what do you want? And I'm like, I want to call this function, but the function doesn't exist. I know, that's why I'm calling it. It's like, what? So that's actually how it feels at the beginning. But it really pays a lot to try it. Because at some point, if you get used into this rhythm, first of all, you get much better confidence in code coverage on your code with tests that you actually have value. I'm not a big supporter of code coverage, but I'm a big supporter of confidence. So you will feel more confident in your tests if you try this. So you write a test, and then you try to run it. And of course, it might not even compile first. So you get it to compile, but still fail. You start by failing. Now, which means that maybe you'll create the function, but force it to return a bad value. My question is why? Why do you think it's a good idea to see the test fail? If you just wrote the function anyway, why actually not make it pass first? Any idea?
If you write the function, you are not sure if it's working or not.
Okay, you're not sure if it's working or not. It's even worse.
Test may pass, but you're not sure that it didn't work before.
Yeah, the test passed, but you don't know if the test is okay. So this is actually how to test the test. You're testing that it fails when it's supposed to fail. And then later, when you fix the function, the test will suddenly become green. So you're testing that the test fails when it's supposed to fail and it passes when it's supposed to fail. If there's something worse than not having tests, is having tests that are lying to you. Tests that are passing and should not have passed. And a test could pass because you forgot to write an assert, or that you're testing the wrong thing, or you're testing a scenario that you think, but you're actually testing a different scenario. So you're testing yourself, that you're actually not lying to yourself. The other thing that happens after the test is failing, then you go into the production code and you implement the simplest piece of code. You are the laziest developer in the world, and you want to go home in 5 minutes. What is the code that you write to make all the tests pass without touching the tests, right? You cannot comment out the test or anything, but you do have to make everything pass. So that's the code that you write. It might not be beautiful, but it will work. And then suddenly all the tests should suddenly pass. You wrote one test, now suddenly it passes. But the code is ugly. So now you go and you make the code beautiful. Now you go and make it more maintainable. But you are making it maintainable after it already passes the test. So now you have confidence if you break something that your refactoring did not break anything. That's one thing that happens a lot in code, is that we're afraid to change it because we don't know if we break something. Or we don't trust the tests that will tell us. But now we do. Now we trust the tests. So we run all the tests. They should continue passing. We do small refactoring, run all the tests continuously, another small refactor. So this is like a mini loop inside the big loop. And finally, we go back to the beginning. So we implemented a very small feature by proving a test is missing, writing a test, proving feature is missing, adding the feature in the simplest form, making it beautiful and maintainable, and then writing the next test to prove the next feature is missing. And it could be one extra feature on the feature we just wrote. Maybe it handles one scenario, now we want it to handle another scenario. And this is a very iterative problem, incremental way of working. And it's very powerful because at any moment in time you have something that partially works. If you stop working on it after 5 minutes, you still usually have 1 or 2 tests that already pass. So you can say that you're 20% done. And the difference between that and doing it the other way, as writing a test and then working on it, writing a function and working on it for a whole day, and then it either works or doesn't work for a whole day, it's completely different than having a function that continuously works more and more during the day. It's a different feeling. So the outer loop, you create code that you trust it works. And the inner loop, you create code that you actually like, that you want to live with yourself in the morning. We all wrote code that we don't want to live with ourselves in the morning, but it works. We cut a lot of corners. Questions about this? The design happens here and there. So when you write the test, you're designing the function, the external function that you call, the parameters, the name of the function. But in the refactoring, you're actually designing internally inside the function. You're designing how the interactions inside objects work and all that stuff. It's really, really important. There are 2 types of design. The upfront design at the top is very important because this is what other people, other developers, other API callers will see. And the inner stuff happens where nobody sees it. But you can change the inner stuff without breaking the top stuff. So I have a function, it takes 2 parameters, returns a Boolean, and internally it might call 17 other functions. Nobody cares from the top. I only care at the bottom that maybe I can optimize, I can change, whatever. At the top it should still work. So internal design and external design. So just really, really quickly, 2 minutes. So if I wanted to write a treasury smart contract, I don't write the treasury smart contract. I write the test first. So this is an example of me writing a treasury smart contract. So I start with this test, right? This is the test I showed you in the beginning. Remember, the smart contract doesn't actually exist yet, so this will not even compile. I try to run this. Forge will say, hey, dude, you're crazy. This doesn't exist. And so I make it happen. I kind of play God. And I say, I wish I could write a test like this and it would magically work. And then you write the contract. And the contract, you have a default balance that is not 0.1, so the test will fail, but it will compile and run. Once it compiles and runs, you see it fail, then you go into the balance and you fix it in the production code, and suddenly the test is green. You move on to the next test. Right? So the treasury at the beginning didn't exist, so I write the treasury, and then I write the receive function. This is all I need to run the test. It actually doesn't do anything. There is no code inside the function. It compiles and it fails. And only then do I make it pass and I add the other function. For example, I say, hey, you know what? I'm actually missing another type of functionality. So when I call join isMember returns true, then I call this function and I assert that it returns true because I called join at the beginning. So imagine I want people to join my treasury. They have to pay 0.1 Ether to join. And so it should say that I'm now a member. This will not work. Why? The function doesn't even exist yet. So I go ahead and I write the function. join, and is member. Now it compiles, right? Now the code here I will not write until the test fails, and only then would I write the code here and the code here. Right? So this is the code where I actually register the member. Notice that I haven't actually checked that they paid the amount, so I can add tests for that, but I don't have to do it in the previous test. I can add another test here. So I have one test that proves join works. I can have another test that says join reverts if you don't pay the amount. And then I have to add the extra functionality. Right? So with payment under threshold, it reverts. So expect revert on error not paid. I call join with 1/10 of what's supposed to be called. So this is my next test that's missing. So I'm proving that this is a bug supposed to work. And then I add the if and the error, right? So I work incrementally on the smart contract along with my tests. It's a continuous incremental work. We're going to finish here. If you have more questions, feel free to contact me. If you want to learn more about this, you can actually get this in a training form. And I really love talking about this stuff. It helps me bootstrap my startup, so feel free to hire me. And if you want to learn more, or if you want to speak about that stuff, even more advanced stuff, you'll feel free to speak about this in our next meetup. So we're going to take a break now. You're going to get some pizza. We have, how many minutes do we want to do? 20, 15, 30? 45 minutes, just kidding. 20 minutes, get some pizza. Thank you very much, everybody.